Hi everyone, I hope you can hear me. Can you please confirm if my voice is audible, if I'm audible or not? Okay, please confirm it and then we will start. Hi Ratul, how are you? So today we are going to start a new subject which is computer networks, right? As all of you might be knowing. So what we will be doing, we will be just solving few of the PYQs just like operating systems. So in operating systems, what I did, in operating systems, I mostly solve PYQs, right? So I mostly solve PYQs. If you have seen those videos, then it is good. Otherwise, that is fine. I mostly solve PYQs, and then if there are some concepts which I think that should be taught in the YouTube classes also, then I took those concepts. So plus some critical concepts, right? Since it is a revision session, so I cannot teach everything in those sessions. That's why just only critical concepts I talked about. For example, I talked about system calls, threads, in terms of concepts. In terms of PYQs, like we have covered everything. And then in terms of theory, I talked about these things, and then threads I have covered. I think this I have covered. Multi-level paging I have covered. Banker's algorithm I have covered. And file system management also, right? So we have covered many of the things in terms of theory also. And in terms of PYQs, we have covered almost everything. Like I think almost all good PYQs have been covered here, right? Now that's the plan for computer networks also, which means like we will be solving some good PYQs, and all along with that we will also be solving or I will be talking about some concepts which are little critical. Okay. So Ratul is asking, sir, are you covering all the PYQs? Just like operating system, we will be covering all the PYQs which are tough in the sense that which are relevant to GATE, and also students find them difficult to solve. So we will be solving all those PYQs, right? So let me get started. So in this session, we are not going to obviously talk about operating system. In this session, we are going to talk about computer networks, right? So this series is for computer networks. Now today we are going to study some topic which is data link layer, and particularly in data link layer we are going to study flow control, right? Now those student who does not know me, let me quickly introduce myself. So we are going to study data link layer, and in data link layer we are going to study this flow control. Okay. So I'm Sachin. I'm co-founder and instructor at GoClasses. I finished my masters from IISc, and after that I have worked at Amazon as an applied scientist, and I also got a GATE All India Rank 33. Okay, let's get started with our topic, which is flow control, right? Now, let me first introduce you two concepts in the flow control, which are stop and wait protocol, and another one is sliding window protocol, right? Okay, so in the flow control, if I talk about the data link layer flow control, so here we have two things. One is stop and wait protocol. Another one is we say sliding window protocol, right? And sliding window is a theoretical concept, but within the sliding window, we have two protocols which are go back N and selective repeat. Now I came to know that few students are just leaving out this computer networks, right? You might be one of them, or if you are not one of them, then it is good. Otherwise, like you might be one of them, so you might be thinking to leave out this computer network. So I will just suggest you to watch these revision sessions. If you're just watching these revision sessions, then I will be covering most of the concepts, and then like you should be able to score something if that is coming from these topics. So basically, if let's suppose computer networks is coming for 8 marks, and if you watch all the revision sessions, and there we will be solving some PYQs, you should be able to score just 5 marks. Okay, this is my target, like just by revision session, and if the question is not too hard, right? So that's in those kind of questions you should be able to score fully. So instead of leaving it completely, it is better to know little bit of it, right? So maybe in just, let's suppose we are going to spend, let's suppose 7 to 8 sessions, and in just maybe let's suppose 10 to 15 hours, if you can score those many marks, then why not, right? Okay, so let me give you the idea of this flow control and these two protocols. So what do happen, that you are a sender, let's suppose, okay, and there is a receiver that is receiving some packets. So what may so happen, that you are sending some packets, but you are sending too fast. Let's suppose you are sending too fast. So receiver might say that, okay, please slow down, right? If you are sending too fast, if you are sending too fast, so receiver will say, please slow down. Or vice versa also. If you are sending too slow, then receiver will say, please fasten up. I mean, you are too slow. So this is what flow control means. Now let's talk about first protocol, which is stop and wait protocol. As the name suggests, it is stop and wait. What do I mean by that? It says that there is a sender, there is a receiver. Okay, so if you send some packet, then this, as the name suggests, that you are going to stop, which means you, once you send some packet, let's suppose there is some packet that you are sending, then after sending this packet you will stop and you will wait for the acknowledgement, right? You are going to wait for the acknowledgement. That's why this protocol is called stop and wait protocol. So you send some packet and then you are going to wait for them for some acknowledgement. Now tell me how much time this whole process takes. Okay, time to send and send packet till receive acknowledgement. How much time this whole process takes? Can anyone tell me? This time is basically called RTT. Okay, round trip time. So round trip time is one time that is basically telling you that how much time you are going to take if you are going to send some packet till you receive one ACK. That's called round trip time. Round trip time. This whole time. And what it includes? It includes many things. First thing, it includes that if you are sending some packet, just look at this picture very carefully. If you are sending some packet, then see here, you are sending, let's suppose, some packet, then there is a first bit. This, let's suppose this is the first bit. You will put that first link, first bit here, right? So see, either you focus on the first bit or you focus on the last bit, which means, I mean, just let's look at this diagram carefully and then you will understand what I'm saying. So let's suppose you're focusing on the first bit, then this first bit from here to here, it will reach from here to here in how much time? It will take TP time, which is called propagation delay, right? So there are two type of times. One is called TP time, another one is called transmission time. I hope you know it, or should I quickly tell you? So there are two type of times. One is called transmission time, another one is called propagation time, right? So transmission time generally we represent by TT, propagation time we represent by TP. So it is basically length upon bandwidth, which means what is the length of the packet? Transmission time is the time to put the data on the link, right? So it is length upon the bandwidth. Propagation time is distance upon velocity. So that's how these two times are defined. Okay, I'm assuming that you know this formula. Now coming here, now if you just, let's suppose this is the first bit. Now if we just focus on this first bit, then this will go from here to here in TP time, but it is just here. Just see here, it is just here. In TP time, it is just here. Now it will take another TT time, another TE time to get it observed. I mean, see, this first bit is just here, but the last bit, let's suppose this is the last bit. Okay, so this is last bit, and last bit is here. Last bit is still here. Okay, so see what is happening, that after only propagation delay, after only TP time, what is the situation? After TP time, your packet is this, right? Package has not completely been observed by B. So let's say B means this is A, this is B. Now it will take another how much time? T time to completely get observed the packet. So basically, if you're focusing on the first bit, then you are saying that okay, this first will go here, but you should be like this B should be absorbing this packet completely. So that's why this is the time that total we take from reaching from starting this packet, transmission of this start of this packet to the B completely get this packet. So for any packet, we are going to take this much time. Now from now onwards, you do not need to worry about that why we are writing TP plus TT. Just think like this, that you are starting this packet transmission till this B get it completely. This is the time that you spend. Or maybe if you focus on the last bit, then you will say that okay, after TT time, see, first you will be writing TT. After TT time, your last bit will be here, your first bit will be here, and then this last bit will get here, here, which means this last bit will be here. It will take TT time extra, right? So this is the last bit now. So basically, this last bit, first you are going to take TT time to place this on the link, and then this is the last bit, right? This last bit is going to take this propagation delay time, which is TP time, to reach here. So basically, this is the time that you are going to take. Either you focus on the first bit or you focus on the last bit, does not matter. So basically, this is the time. Now we are going to say TP plus TT is the time that is called round trip. Sorry, this is not round trip time. I mean, you will send the ACK. That whole time is called round trip time. But anyway, this is the time that any packet takes from start of the transmission till B completely get it. Okay. So this is very important time. So TT plus TP, this is the time any packet takes from very start of the transmission to other host get it completely. Okay, so this is the time. Now there is now this B will do what? This B will send the ACK, and let's assume the transmission time for the ACK is almost 0. So this B will send the ACK, and then there will be another propagation delay that you are going to take. So there will be another propagation delay that you are going to take to receive the acknowledgement. So after this much time, you will receive the acknowledgement, right? So this much time is called RTT time. Now let me define this RTT. That's very important. Round trip time. It is a time where you are going to start sending a packet. I mean, you think about that you just want to send the packet, right? The moment you think means like the moment you start the transmission till the point you get the ACK, that's the time this RTT is, which is TP plus TT for the packet, and then one more TP, which is for the acknowledgement, right? So this is called round trip time. Okay. Now what may so happen that in between there could be some routers or something, there could be queuing delay, there could be processing delay. If you have those kind of things, then you can add those processing delay, queuing delay, these kind of delays, right? If you have. Otherwise, generally we do not have these delays. In the test series, definitely, like in the test series, just for the sake of practice, we will give you. Okay. So I hope that is understood to everyone. Now that's very interesting time. This time, which is 2TP plus TT, this is very interesting time, which is called round trip time, and it is very interesting. Why I'm calling it interesting? Because on this basis only the whole story is revolving. So basically, this is the time that you start sending the packet till the time you receive the packet, right? That's called RTT. Now let's just see that what we can do in this time. So basically, this is the time that you are going to invest, right? This is the time that you have invested to send how many packets. If you're talking about stop and wait protocol, then in this time you have sent how many packets? Just one packet, right? I mean, you sent one packet, you are waiting till the first ACK get arrived. I mean this ACK get arrived. So in stop and wait, in this time you are sending just one packet. Okay. Now, out of the context, if I just ask you one question, now suppose this TT is the transmission time, right? That you know, transmission time. Suppose out of the context, if I ask you one question, that how many packets, how many packets you can transmit in 5 TT time, then what is your answer? What you will say? How many packets you can transmit in 5 TT time? Just let me know quickly. Okay. Definitely you can send 5 packets, right? 5 packets. But how you did it? You must have taken this 5 TT and whatever time I'm asking, then you must have divided it, right? These many packets you can transmit. Similarly, if I ask you the question that how many packets you can transmit in 2 TP plus TT time. How many packets you can transmit in 2 TP plus 2 TT time? What will your answer? See, if I just ask you for 5 TT, then what you did? You divided the number with the 5 TT, right? And similarly, you will be doing the same thing. You will say the number of the packets that you can transmit, number of packets you can transmit in this much time is actually equal to 2 TP, right? 2 TP plus TT. I hope that is visible. So let me just write it here. 2 TP 2 TP plus TT divided by TT, isn't it? Let me know if that is clear to everyone. Yes. So this will be 1 plus 2 TP upon TT. Can anyone tell me that what do we call this number? TP upon TT? We call this A. Okay. So these many packets you can transmit in this much time, right? Okay. Let me ask you one more question. Similar question, almost similar question, that how many packets you can transmit in just TP time? Okay. In just a TP time. What you will do? You will divide by TT, right? So these many packets you can transmit in just TT time, and that's what we call A. A just some notation, right? So you will say these many packets TP upon TT. Let's just call this number as A. Okay, this is just I'm just calling it A. There is no significance. It is just that you can transmit these many packets in TT time, like sorry, in TP time, in propagation delay time, which means whenever sender is sending, and the moment this whenever sender is sending something, right, this is the start. The moment this packet reaches here, which means in TP time, he could have sent a number of packets. So basically in this link you can put a number of packets. The moment this packet this bit get reaches till the end, like this, and till this moment you can put a number of packets. Are you getting my point? See, you started the transmission, and the moment this was the first packet, the first packet reaches till the end, the last bit or the first bit, whatever, right? This reaches till the end, just to the B. I mean, B has not completely observed it, right? B just saw the first bit, right? This is the first bit of the first packet. The first bit of the first packet, the moment it reaches to B, till that time you can send a number of packets, which means it is called a link capacity, which basically you can fill this link with the A packets. You cannot fill more than A packets, right? If you put A packets, by that time the link will be full, isn't it? The moment this bit reaches here, this will be TP time, and by that time you can put a number of packets. That's why it is called link capacity. Let me know if that is fine to everyone. So A is very special number that is called link capacity in the sense that you can put a number of packets by the time the first packet reaches till the to the B. I hope that is fine. So you can fill the link with a number of packets. Can you put more than a number of packets in the link? Never, right? So we can never put neither a plus 1. Can we? Okay, let me just ask you. Can we put? Can we put uh, a number of packets? Let me first ask you a number of packets in the link. What is your answer? Can we put a number of packets in the link? The answer is yes. Yes, we can put a number of packets in the link, right? Now, similarly, if I just ask you, can you put a plus 1 number of packets in the link? A plus 1 number of packets in the link. Then what is your answer? Can you put one more packet apart from A? Can you put one more packet? Then answer is no. Clearly no, right? You cannot put a plus 1 packets. So this is called link capacity. Link capacity means that you can at most put a number of packets in the link. I hope that is okay with everyone, right? So you understood this, right? So you cannot put more than a, like a plus 1. No, I cannot put. So this, yeah. So this number is quite interesting. So I was talking about this 1 plus 2a. This 1 plus 2a is the number of packets that you can put in this much time. So you have this much time in your hand. In this much time, you could have sent 1 plus 2a, but you are just sending one packet, right? So tell me, see, you have this much time in your hand, 2tp plus tt. Now tell me the number of packets, okay, in terms of packets, tell me number of packets we can send in this much time. That will be equal to 2tp plus tt upon tt. That will be 1 plus 2a, isn't it? Isn't it? Okay. Is this fine to everyone? Now, okay, I hope I'm audible, right? Now just tell me, this is 1 plus 2a, which is number of packets you can send. Now, instead of asking you number of packets, if I just ask you number of bytes, I mean how many bytes you can send, right? Number of bytes we can send. Number of bytes we can send. Tell me. See, if I just ask you number of packets, you just told me this is 1 plus 2a. If I just ask you how many bytes you can send, can you tell me this is the same thing in the bytes? See, this is the time. And you have the bandwidth with you. Bandwidth means that bytes per second, right? Bytes per second. If you multiply with the seconds, you will be getting the bytes, that these many bytes you can send. So, see, what does the bandwidth tell you? Let's suppose bandwidth is 500 bytes per second, which means in 1 second you can send 500 bytes. And what I'm asking is that in these many seconds, how many bytes you can send? So you will multiply with the bandwidth. So bandwidth into 2tp plus tt, right? So these many bytes, in terms of bytes, you can send these many bytes. In terms of packets, you can send these many packets, right? I hope this diagram is clear to everyone. And that is this number is called bandwidth delay product. This number is called bandwidth delay product. Okay. Cool. So now since you know this, now tell me, can you convert one from another? Which means you know in terms of packet, you know that 1 plus 2a. Now can you tell me in terms of bytes? I think that's also easy, right? Let's suppose if I tell you that 1 plus 2 is how many bytes. If I just ask you 1 plus 2 is how many bytes, then what you will say? Let's suppose one packet is L bytes. Okay, the one packet is, let's suppose the length of the packet is L. If I just tell you the length of the packet is, let's suppose L. If one packet is L bytes, then can you tell me how these many packets are how many bytes? Into L, right? So you will say this is into L bytes, right? Which is L into 1 plus 2a bytes, right? So in terms of bytes, also you can calculate from this above number, or in terms of packet you already know. Then these two numbers must be equal, isn't it? Are you getting my point? See, you have calculated in terms of packet and you have calculated in terms of bytes also. Now what I'm saying, that these two numbers must be equal. What is the first number? First number is L into 1 plus 2a. Another number is this. Can you just tell me whether these two numbers are equal or not? Okay. Must be equal, right? Can you just tell me how these two numbers are equal? Or maybe you can just expand this a, which is tp upon tt, and from that if you just calculate it, this will be 2 tp plus tt upon tp, and then I mean if you just solve it, it will be L upon basically L into 1 plus 2 into tp upon tt, and then finally if you just do it, tt into L is just bandwidth, because tt formula is L upon bandwidth, right? So yeah, okay. So basically, yeah, L upon tt will be just bandwidth. So it will be same as bandwidth into 2p, 2t. This is t, this is p. Uh, t tp upon tt, right? tp upon tt. Yeah. So this you multiply. Yeah, that is correct. 2tp plus tt into bandwidth. Yeah, you will be getting this number, isn't it? These two numbers are same basically. So I hope you understood. Anyway, like I don't want to go this kind of calculation, but actually these two ways are just same. I mean, there are no different. Okay, either you calculate in terms of bandwidth, or you calculate in terms of packet, or I mean you calculate in terms of bytes, or you calculate in terms of packet. But the key idea is that you should be knowing that how to calculate, right? So basically, given this time, this is the very important time, which is called RTT. This is the time that you have, time that we have, right? Which means this is the actually total time that you are going to take from the moment you start the transmission till the moment you get the ACK completely, right? So from the moment you start the transmission, this is the total time. This is the total time that we have from the moment we start the transmission to end, right? We get the ACK. I hope you understood this. So this time is very, very important. 2tp plus tt. Okay, and on this time only the whole picture is revolving. So this is the time, the total time from the moment, basically total time from the moment we start the transmission till we completely get the ACK. Okay, and during this time what you are doing is basically depends on I mean that will define your efficiency of the protocol. So basically this is the total time that you have. If you, and in this time you can send these many packets, or in terms of bytes also you can find out, you can send these many bytes, but let's just stick to the packets. Okay, so you can send these many packets, and how much you are actually sending will define your efficiency. So what is the efficiency of stop and wait protocol? Will be, since you're just sending in this much time, see this much time you have in your hand, right? uh, this much time you have in your hand, and in this much time you are sending just one packet. You are sending just one packet, and you could have sent 1 plus 2a packets, isn't it? Or maybe in terms of bytes also, you could have I mean, you are sending just l bytes, and you could have sent how many bytes? This is, I mean, you just need to multiply with this. You could have sent these many bytes, isn't it? Which is same as 1 plus 2 actually. So that's why I will not write this thing. I will be just writing 1 plus 2, 1 upon 1 plus 2. So that's called efficiency. Efficiency means what you are actually sending, what you are actually sending, or what you could have sent. So this is the formula of efficiency. There is something called throughput. Throughput, as the name suggests, it is basically that in 1 second, or in like in any unit of time, how much bytes or the packets you are sending. I mean, it depends that you are talking about the bytes or the packets, but yeah, in 1 unit of time, in 1 unit of time, how much bytes or packets, I mean, it depends on your unit basically, packets we are actually sending. Which means, okay, which means if I just say the throughput, okay, if I just say that throughput is, maybe let's suppose I say 5 packets per second. Is this a valid unit of the throughput? Tell me, is this a valid unit for the throughput? Definitely, right? This is definitely a valid unit for the throughput. If I just say that, okay, it is maybe, let's suppose if I say 300 bytes per second, is it the valid unit for the throughput? Yes, this is also valid unit for the throughput. I mean, it depends that how you're defining the throughput. It is basically some quantity that you are sending per unit of time. Okay. Now tell me, is this a valid unit of throughput? 200 packets per minute. Yeah, this is also valid unit for the throughput. So basically it is saying that in 1 unit of time, maybe in per minute, per second, per microsecond, whatever, right? In 1 unit of time, how much data you are sending, how much packets you are sending, how much bytes you are sending, it depends on you, like how you are measuring it. It is not very hard and fast rule that you should be doing like that, right? Only, okay? So that's how the throughput is defined. Now, since you know the efficiency, which is 1 upon 1 plus 2a for the stop and wait, okay. Now let's just talk about the throughput also, and then we will start solving some questions, okay. So now let's just talk about throughput, okay. Can you tell me that how we can calculate the throughput? So basically tell me how many bytes you are sending, or maybe see, it is basically bytes per second, right? So you can say that in this much time, okay. I mean, okay, let me just give you the hint. Let me just give you the hint how to calculate this throughput. It is very easy idea to calculate the throughput. Okay, I will leave it to you. I mean, just for a moment, and then I will solve it. Okay, let me just give you the hint, which is something like this. In 2 TP plus TT time, TT seconds, let's suppose, okay, seconds, we are sending that is equal to maybe 1 packet, okay. I mean, it depends on how you are calculating 1 packet. So now tell me, in 1 second, how many packets you are sending? Okay, that's the throughput is, right? See, throughput is very easy. In 1 second, in 1 unit of time, what you are doing, that's called throughput, right? So, or maybe 1 packet, if you want to talk about the bytes, then let's suppose L bytes. Now tell me, in in 1 second, how many bytes or packets, anyway, like, does not matter, okay. Let me talk about the bytes. How many bytes we are sending? Can you tell me the answer? How many bytes we are sending in 1 second? Okay, let me know. So that's not a very tough question. I'm just asking that how many bytes we are sending, right? Yeah, that is L upon RTT. Yes, absolutely. So basically we are sending L upon 2TP plus TT, right? So that's what throughput is. That is throughput. So why I'm telling you so much of detail instead of directly telling the formula? Because you should be knowing these details. It may not be like the formula may not be directly applicable, or they may play with the words. In that case, you should be knowing that what is the actual meaning of the throughput and all, right? So now the throughput you have just calculated, which is L upon 2TP plus TT. So this is called throughput, which means these many bytes you are sending per second, right? Now, okay, now this is the efficiency, this is the throughput. Can you convert one from another? Can you just tell me what could be the relationship between efficiency and throughput? So this is the efficiency which I can rewrite in another form, which means in TP, TT also I can rewrite. Okay, so this will be efficiency, I can rewrite it. This will be TP upon TT. So this will be TT upon T2TP plus TT, right? And now this TT is also I can rewrite L upon bandwidth, right? So L upon bandwidth into 1 upon 2 TP plus TT. So L, let me take L there. So now can you see, the similarity between the throughput and the efficiency? This is the throughput that we have, right? This is the throughput and this is the efficiency. Now can you tell me the how to convert from throughput to efficiency? What is the relation? See, this efficiency is this, sorry, this is L. Efficiency is L upon this much, and this is just a throughput, right? So you can say the throughput, efficiency and throughput both are same. It's just a difference of bandwidth. So I can say that the finally I can establish a equation which is basically saying that throughput is equal to efficiency, generally we represent by like this, into bandwidth, right? So that's what throughput is, and that is also logical, that how much efficiently we are using this bandwidth, it is the throughput, right? That is correct. So that is what throughput is. So now let me just tell you that what we have been doing. So you might be knowing all of this, like honestly I know that you might be knowing all of this, but if you have not studied from Go classes, then maybe like I mean, in that way you might not be in, you might not have studied, right? And if you have studied from Go classes, then it is just a revision for you, right? Okay. So I hope everyone is with me. Everyone is on the same page that what we have been doing. So I just defined one number which is RTT, and I'm saying this is your RTT, and then I'm saying in this much time how much packets you could have sent, which is what we have called 1 upon 1 plus 2a, and then we talked about that this is the number of packets. Then we talked about what if I ask you number of bytes, then also you can calculate in this much time how many bytes you are sending, or in this much time how many packets you are sending, right? You can talk about either of them. And then we talked about the efficiency and then throughput, right? Efficiency is basically how much you are actually sending, and how much you could have sent. That's called efficiency in the given time, right? This is the time that you have, how much you are actually sending, how much you could have actually sent, right? This is the total maximum number of things that you could have done. So that's what stop and wait protocol is. And then if I just summarize everything, so you will say efficiency in stop and wait is this: A is equal to TP upon TT. That's all, right? And then throughput is equal to bandwidth, efficiency into bandwidth. So these are the just two small formulas that we need to remember for the stop and wait. Now similarly, for the sliding window protocol, we just replace this one. Okay, for the sliding window protocol, we just replace this one with the window size, right? So this is sliding window protocol. So sliding window protocol are of two types, which is go back and selective repeat. In both of them, we have the same efficiency. Now, can anyone tell me, very interesting point, if both of them are having the same efficiency, then what's the use of, yeah, I mean, what is the advantage of one over another if both of them are having the same efficiency? Can anyone answer this question? See, it is basically because if you are having noisy channel, in that case the go back and efficiency will be lesser. These are the efficiencies if the channel is not noisy. If the channel is noisy, then it is not easy to have the closed form formula of the efficiency, and in that case the go back and is obviously not a good idea, right? Okay. Now, let's solve some of the questions, and maybe after that you will be more confident. So what this question is saying, a channel has a bitrate means the bandwidth, okay? Bitrate of 4 kbps, right? Let me write the bandwidth is given to us is 4 kbps. One way propagation delay, which means the propagation delay is given to us is 20 millisecond. The channel uses stop and wait protocol. The transmission time of the acknowledgement frame is negligible. So generally it is the case that transmission time for the acknowledgement frame is always negligible. Okay, you do not need to worry about the transmission time for the acknowledgement. The transmission time for the acknowledgement frame is negligible. To get a channel efficiency of at least 50%, the minimum frame size should be. So they are asking about what should be the L such that your efficiency is minimum 50%, which means greater than or equal to 1 by 2. Okay. So what is the formula of efficiency? Efficiency is 1 upon 1 plus 2a in the stop and wait. It should be greater than or equal to 1 upon 2, isn't it? Now from here you can easily calculate that 2a, I mean 1 plus 2a is less than or equal to 2, which means 2a is less than or equal to 1, which means a is less than or equal to 1 by 2, right? So let me go to the next page. So here a should be less than or equal to 1 by 2, and a is Tp upon Tt. So that is why it should be less than or equal to 1 by 2, which is same as saying Tp. Is this given to us? Yes, 20, right? So uh, okay. So basically you can say this Tt is greater than or equal to 2 Tp, right? Yeah, that is correct. And then this Tt is L upon bandwidth should be greater than or equal to, it is given to be 20 into 20, greater than or equal to 40 milliseconds, and then this is L upon bandwidth. Bandwidth is also given to us, so that's why you can find out L, which is greater than or equal to 40 into bandwidth, right? And what is the bandwidth that is given to us? It is 4 kbps. So this is in the millisecond, this is in the millisecond, this is in the 4, this is 4 kbps, kilo bits per second. Now can you get me the final answer? So millisecond, let me just convert this millisecond also to the second, because this is in the second. So that's why let me convert that to second. So that is why it is 40 into 10 to the power minus 3 into 4, because of the k 10 to the power 3 into because 10 to the power 3, and then this is in the second. So I think this will get cancelled out. This is 160 160 bits, right? 160 bits, because it is bits, right? I hope you understood. Let me know if there is any doubt. Okay. So now let's move to another problem, right? So 160 bits is the answer, and you can check the answer. D should be the correct answer, right? Cool. So let's move further. Yeah, D is the correct answer. Now what this question is saying, on a wireless link, the probability of the packet error is 0.2. So they are saying that I mean, whenever you are sending a packet, that could be error, there could be error in the packet, is the probability is 0.2, and that link is wireless. I mean, that is okay. A stop and wait protocol is used to transfer the data across the link. The channel condition is assumed to be independent of the transmission to the transmission, which means whenever you are sending a packet, first packet you sent and the second packet is sent, like there is no relation between these two packet transmission, right? What is the average number of transmission attempt required to transfer 100 packets. So they are asking what is the average number of packets that you want to send, that you have to send just to send 100 packets. So what is the question? Question is saying that you want to send 100 packets, right? So there are 100 packets that you want to send, but the problem is that you will not end up just sending the 100 packets. You will say that you have to send maybe more than 100 packets, because one of the packet, maybe the first packet can get some error. The probability is 0.2. Okay, so basically these 100 packets you have to anyway send, but plus you have to send something extra, right? Is this okay to everyone? Is this understood what I'm asking? So basically they are saying you anyway have to send 100 packets, but you have to send something extra. That extra is basically retransmission of some packets, retransmission of some packets, right? So I hope you understood this question. Now actually, before solving this question, let me just solve this question, which is quite similar to this question, and these two questions are very much relatable. You will get to understand that why I am saying so. Okay, suppose there is a coin toss. The probability of head is 0.8, probability of tail is 0.2. Now what I am saying, what is the expected number of tosses for one head to come? So what I'm saying, there is a coin that you have, right? There is a coin. You toss it. Either you get the head, you get the tail. If you get the head, then obviously there is just one toss that you perform. So that's why the expectation in this case is just one. But if you get the tail, then what you will do? You will restart your process, which means you will again do the same thing, and then you will again toss it out. Then you will check whether it is a head or it is a tail. If it is a head, then total number of the tosses that you did is just 2. But if it is a tail, then you again have to do the same thing, isn't it? Are you getting my point? What I am trying to convince? So basically, you toss it out. Either you will get a head or you will get a tail. If you're getting head, then you will stop here. If you're getting tail, then my question is you need to find out the expected number of tosses to get the head. If you're getting the tail, then you will again toss it out. Then if you get the head here, then the total tosses that you perform is 2, and if you get the tail, then you will again doing the same thing. So let me just solve this question, and then we will get back to that question. So basically here, let's suppose I did till this point. So here, can you tell me the number of tosses till head? I mean, if you get head, then it will be 1. If you get tail, then what is the number of tosses? Let's suppose initially, like I'm initially here when I'm not tossed. The E is my answer. Okay, E is my answer, which means I'm saying that total number of the tosses that you need is E. Okay, total number of the tosses that you need is E. Okay, suppose this is the answer. Sorry about the disturbance. Suppose this is the answer, then you will say that if you are getting tail, then you have to restart your process, right? This is the restart of the process. Since this is the restart of the process, that is why you will say again you have to perform just E number of tosses. So basically, with this probability, 0.8 probability, you are going to perform. So you will say E is equal to, basically I mean, I don't want to go too much of detail. Like if you are goclass student, then I'm 100% sure that you must have recalled these kind of questions. Can anyone tell me if you can recall these kind of questions? We did it thoroughly, right? We did many variations of these kind of questions. We did TIFR questions. We did gate previous year questions based on the just this kind of phenomena. So basically, in general, it is like this: E equal to some probability. So I mean, some event happen. Okay, probability of event. If event happen, then what is the expectation? Plus if event does not happen, then what is the expectation, right? So plus if event not happen, event. Okay, this is E1, this is E2. So this is a general formula that is called total of expectation. But anyway, that is fine. I mean, you do not need to know this formula. So basically, here if you want to calculate this E, then if event happen, then what is the number? That is 1. If event does not happen, which is 0.2, then what is the number? It is E, right? So instead of writing 0.8, 0.2, let me write probability of head and 1 minus probability of head. So basically, let me go to the next page. So either you get a head or you get a tail, right? So here the probability, and let's suppose this is 1 minus P. Okay? So you are saying that here you need just one toss, here you need E tosses. So E should be equal to, if P into 1 plus 1 minus, with 1 minus P probability, you need E tosses. So if you just calculate it, then the expected number of tosses will come out to be 1 upon P. Okay, that is also called geometric distribution, but anyway, you do not need to know that distribution. So this E is called 1 upon P. E is coming out to 1 upon P, which means that the number of expected number of tosses that you need, if the success probability, okay, that is actually that will come again and again, that's why I have told in the detail. If the success probability is P, if the success probability is P, then expected number of trials, to get success is actually 1 upon P. That's what I want to say here. Okay, in short, I hope you understood. Now the success could be anything. Success could be tossing a head, or maybe getting the head, getting the tail. Success could be sending a packet, receiving a packet, or whatever, right? If the success probability is P, then the total number of trials to get that success is 1 upon P. Now tell me, if you are sending a packet, it gets successfully delivered, the probability is P, then how many, just one packet, okay, then how many packets on average, or expected number of packets that you need to send to just send one packet, it is 1 upon P. So basically, just to send one packet, we have to send 1 upon P, and here P is equal to 0.2, I think, right? So which means that 10 upon 2, which means 5. Just to send one packet, you have to send 5 packets, right? If P is 0.2. Okay, probability of error, probability of error is 0.2, then what does this mean? Probability of successful transmission is 0.8, right? Probability of successful transmission. So if probability of success is 0.8, then you will say, just to send one packet, you need 10 upon 8 packets, right? Just to send one packet only. Now to send 100 packets, you need to multiply by the 100. So from here you will be getting 125, which means just to send 100 packets, you need 125 packets. So you need 125 packets. You have to send 125 packets to just send one packet. I hope you understood this. Let me know if there is any doubt here. Right? Okay. So that is okay to everyone. Now let's just go to the next problem. Okay, correct answer is B, or maybe you can solve in some other way, but that is fine. I mean, the final answer should be the B. See, this is a similar question, and just to get one head, you need 1 upon P trials, and just to get 100 heads, you need these many trials. Okay. Now let's solve this question. What it is saying: a sender uses stop and wait ARQ protocol for reliable transmission of the frames. The frames are of size 1000 bytes, and the transmission rate of the sender is 80 kbps, right? The size of the acknowledgement is 100 bytes. So they are saying that the size of the packet or the frames is 1000 bytes, and the transmission rate, which means that I think they have given the bandwidth, which is given to be 80 kbps, means K means kilo. So yeah, let me first write kbps only. See, this is in the bytes, this is in the bits, so you have to be careful. Size of the acknowledgement is 100 bytes. Okay, so acknowledgement length is also given here. Generally they do not give, but yeah, here it is given. It is 100 bytes, and the transmission rate at the receiver. Okay, receiver is transmitting at 8 kbps. So transmission rate at the sender and the receiver both are different, which means that if receiver have to send some packet, so basically this is interesting question. What they are saying, this is A to B. If A has to send some packet, then there is a different bandwidth that is given to us, which is 80 kbps. If B has to send some packet, then this is also given to us, which is separate, right? This bandwidth is given to us, which is separate. It is given to be 8 kbps. The propagation delay is 100 millisecond in between A and B. The propagation delay is same irrespective of the bandwidth, obviously, is 100 millisecond. So let me write the propagation delay, which is 100 millisecond. Now, assuming no frame lost, the sender throughput is, okay, that's very nice question. So they are asking the sender throughput, bytes per second. Now tell me how much time you are total taking. Okay, so you are using stop and wait. How much time you are total taking? So what are the times you are taking? Can you tell me? See, you will send a packet, right? So for the packet you will be taking TP plus TT, and then you will be receiving an acknowledgement. Generally we do not count the transmission time for the acknowledgement, but here you need to count, right? So the total time you are spending is this 2 TP plus time for the packet plus time for the ACK, also transmission time for the ACK, isn't it? This is the total time that you are spending. Let me know if that is fine, right? So this is the total time we are spending. Now what is this 2 TP? I think you can easily calculate 2 into 100, right? Plus TT. TT here at the, I mean when you are sending a packet, which means it is 100, right? 100 upon 80. You need to convert that to byte. So maybe you can convert, yeah. So I think you can convert this to bits, and does not matter. I mean whatever you do, and then you need to 80. This is kilo, and yeah, this is in bytes. So since it is kilo, so I mean kbps, so you need to convert that to just this one. This is in bits, right? This is bits, and then now it is bits per second. So final answer will be in the second, and this was in the millisecond, right? This total thing is in the millisecond. So that's why this is in the second. So that's why you need to multiply by 10 to the power minus 3 to get this also in the millisecond. So it will be 10. It will be 10 to the power minus 4 milliseconds. Sorry, since it is seconds, so yeah. To convert into the millisecond, you need to convert. You need to multiply by 10 to the power 3. So it will be 100, right? So it is 100 milliseconds, which is this. This quantity is coming out to be 100 milliseconds. Is this understood, or should I do it again? And now you need to calculate this final quantity, which is time for the ACK. So let me write TACK. I mean transmission time for the ACK. Length of the ACK is given to us, which is 100 bytes. Let me convert it to bits upon 100, right? Sorry, length upon bandwidth. Bandwidth is 8 kbps. So 8k means 10 to the power 3. It is already in bits. So this total time in the second. So that's why in the millisecond it will be this much. So it is also 100. Yeah, so both are coming out to be 100. So total time that you are spending is how much? 200 and 100 and 100, which is 400 milliseconds, right? So in your hand, right, the round trip time is coming out to be 400 milliseconds. Let me know if that is fine to everyone, if this all of this is fine, or there is some issue. Right now, in these 400 milliseconds, how much you are actually sending? So basically in this 400 milliseconds, they are saying the throughput means whatever you have in your hand, in these how much bytes you are sending. You are just sending the one packet, right? One packet length is 100, sorry, 1000 bytes. You are sending 1000 bytes. So 1000 bytes upon 400 millisecond, and let me convert that to, this is bytes, let me convert it to seconds also. This is 10 to the power minus 3 if you convert that to seconds. So basically this is seconds. So this is your throughput, isn't it? So here they have given two way different one, I mean this way and this way. Now you just need to calculate that, okay, this much data you are sending and how much time you are sending. You are sending 1000 bytes. In terms of bytes, you are sending 1000 bytes in this much time, right? So that's why this is your throughput. Now if you calculate it, it will come out to be 10 upon 4, 10,000 upon 4, which will be 2500, right? 2500 bytes per second. Let me know if that is fine or there is some doubt. Sumant, Devanjan, Ratul, is this okay to everyone? Okay, so I hope that is fine. Let me just see the answer also. Yeah. See, they have calculated the total time. In this total time, how much bytes you are sending? This much bytes. So that's how you can calculate the throughput, right? Okay, cool. Now let's move to the next question. If that is understood, let's move to the next question. So basically, the key idea is that you should be knowing that what is the throughput. Once you know what is the throughput, then all of this confusion will go away, right? So here, what is happening? See, here what is happening? They have given, this question is little interesting. They have given two side bandwidth, okay, A to B, and B to A also is given to us. They have given two side bandwidth. This bandwidth is different, and this bandwidth is also different. So this bandwidth they have given to us, which is I think 80 kbps, and this is 8 kbps, right? This is 8 kbps. Now, what you can do, I mean, you want to find the throughput, right? So I have found out the throughput using the using the intuition. Like I mean, these many bytes you are sending in this much time. But you may tend to use this. You may tend to use this formula. So efficiency you can definitely calculate. This is 1 upon total RTT, right? You are sending one packet in total RTT. So RTT was I think 400. Um, yeah, 400 millisecond was the RTT. So you can say that okay, this is your efficiency, right? 400. Sorry, uh, your efficiency will be, yeah. Will this be the efficiency? Tell me. Tell me what will the efficiency? So efficiency is that how much. Basically, efficiency says that that I mean this is basically how much you are actually sending upon how much you could have actually sent. This is how we calculated the efficiency earlier, right? This is how we calculated the efficiency. Here the I mean we have ignored too many of the things. So how much you are actually sending, that is one only, but how much you could have actually you could have sent, it might not be 1 upon 1 plus 2a, right? So the total RTT, so here you also need to calculate the efficiency separately. So the total RTT that you have is something, I mean something different, which is 400 millisecond. In that, how much you could have actually sent, you need to divide by, okay, you need to divide that by transmission time at A. And what is the transmission time at A? It is 100, right? So anyway, like this is 100. So basically, you will say that 1 upon 4, your efficiency is 1 upon 4, right? How we are calculating, can anyone tell me? See, I mean, I do not want to go with the formulas and all, but if you are really interested in going the formulas, then you can drive the formula for efficiency. Efficiency says that how much you are actually sending, which is 1, okay? We are in stop and wait, we are always sending 1, actually sending. We are actually sending 1. How much we could have sent in RTT, right? Number of packets we could have sent in 1 RTT. So what is RTT? RTT we just calculated, it is 400 millisecond. And now in these 400 millisecond, you could have sent, since the transmission time at A, okay, not at B. I do not even care about the B, because you want to transmit at A, right? The packets, you are just seeing the number of packets. You can transmit here with the 100 millisecond. I mean the delay is the 100 millisecond. So do you remember, like we divide by TT, right? See, if I just ask you how many packets you can send in 5 TT, then you divide by TT, right? Then you find out that okay, 5 packets you can send. Similarly, if this much time in your hand, then you divide by TT. TT is 100, so 4 packets you could have sent, right? So 4 packets you could have sent. So that's why the efficiency is 1 upon 4, right? Now once you get the efficiency, which is 1 upon 4, this is the efficiency that you have. Now what I'm interested in, that the throughput at A, right? So here you will be using the bandwidth of A, since there are two bandwidths that you have here, which is 8 kbps, and this is, sorry, this is 80 kbps, this is 8 kbps, right? So you need to use the bandwidth at A, because the throughput you want to calculate it at A. So that's why the throughput will be, just a second, should be efficiency into bandwidth. Okay. Yeah, I think should be, let me just check. So efficiency is 1 upon 4 into bandwidth is given to us 8 kbps, right? 8 into k means 10 is power 3, and they are asking the throughput. Let me check. They're asking the throughput in the bytes. Okay. Since it is in the bits, right? This bandwidth is in the bits. That's why you need to convert that to a byte. So now it is in the bytes. Okay. Yeah, it is now bytes, and k I removed the k, and it is in the bytes per second. Yeah, that should be the answer. It is in the bytes per second, right? This throughput is in the bytes per second. So here, if you calculate again, um, this is 250 and 10 should be there. Okay, this is 80 actually. This is 80. This is not 8, this is 80. So final answer is 2500 kb, sorry, bytes per second. But anyway, I mean, you can do the form, you can do using the formula, but using the formula it will be little tough, right? Tough in the sense that this is not intuitive. You are unnecessarily using the formula. First, you need to drive the efficiency using the formula, because the formula is not anymore 1 upon 1 plus 2a. So basically, efficiency says that you need to go intuitively, that 1 upon what we are actually sending, the number of packets that you could have sent. So that's how you need to drive the efficiency first. Once you get the efficiency, you need to multiply by the bandwidth, right? Then you can do it that way also. But yeah, I mean, if you directly use the intuition, which is that, okay, this much time you are taking, and in this much time, how many bytes you are sending, just calculate it, right? In this much time, how many bytes you are sending. So that also, that is how also you can do it. I hope you understood both of the ways. I will prefer that you know the intuition, then it is very easy, right? I will prefer that you should be knowing the intuition. Is this okay to everyone? Okay. Now, now let's just move to another question, which is this. Okay. So this question is dealing with some full duplex. Let me just check. This question is related to sliding window. Now we are solving the questions related to sliding window. So we just finished the questions related to stop and wait, and these questions are related to sliding window. But yeah, I must appreciate this question. This question was very good, in the sense that they have used the two-way bandwidth separately, and then they're asking few things, right? That question is really appreciable. If you're from Go classes student, then you might remember it, that there was one question that we have solved in the similar, that was of similar pattern, that was from MIT, right? I mean, you might recall it. Like, we solved a similar question. I did not know that at that time that question has been asked in GATE also. Okay. So now let's just solve this question. Host A is sending a data to host B. Host A is sending a data to host B with the full duplex link. Full duplex link means that B can also send the data to A. Okay. A and B are using the sliding window protocol for the flow control. Okay. And like, they are using the sliding window protocol. The sender and receiver window size are given to 5 packets each. So here the window size is given to 5 packets, given to be 5 packets here, and the receiver window size is also given to be 5 packets. 5 data packets sent from A to B are 1000 bytes long, and the transmission time for such a packet, so data packets length is given to be 1000 bytes, and transmission time is also given to us, which is 50 microseconds. Acknowledgement packets sent only from B to A, okay, are very small and require negligible transmission time. The propagation delay over the link is 200 microsecond. So they are saying the propagation delay is 200 microsecond. Now, what is the maximum achievable throughput in this communication? Okay, so they are asking about the throughput. Now, can you calculate the efficiency here? I think this is very easy question. You can just calculate the efficiency, which is 1 upon the size of window in case of sliding window, size of window 1 plus 2a, right? This is the efficiency that we have. Now, which will be equal to 5 upon 1 plus 2 into a is equal to TP. What is TP? This is 200 microseconds upon TT, which is 50. So I think it is 4, right? So yeah. So I think this is 5 upon 21. This is the efficiency that is given to us, isn't it? So I think yeah. So based on the data that we can calculate, the efficiency is 5 upon 21. Or there is something that is missing. I think that's the only thing, right? Sorry, 5 not 21, 5 upon 9. So this is the efficiency that we have. Now, once you have the efficiency, which is 5 upon 9, what we need to do? We need to calculate the throughput. Can you tell me how to calculate the throughput? It is efficiency into bandwidth, right? So what is the bandwidth here? Is this given to us? I think bandwidth is not given to us. So you can calculate the bandwidth using the transmission delay. So using these two data, you can calculate the bandwidth, right? So let me just do it. So bandwidth is equal to basically the transmission time is equal to length upon bandwidth. So that's why bandwidth is equal to length that is given to us, which is 1000 bytes upon transmission time is in microsecond, right? Which is 50 microsecond. So 50 microseconds, it is in bytes. Okay. And this efficiency does not have any unit. So finally, efficiency into bandwidth. This is the bandwidth. So bytes per microsecond will be the answer, but they are asking the answer in bytes per second. So since they are asking the answer in bytes per second, so let me just convert that to seconds. So it will be 10 to the power 6, right? That is why the answer is 5 upon 9 into 10 to the power 3 upon 50 into 10 to the power 6. This is bytes per second. So that is why this will be 10 to the power 3. This will be 10. So this is 1 upon 9 into 10 to the power 4 bytes per second. Let's just see. 1 upon 9 into 10 to the power 4. Something I think, okay, this is microsecond. You can, okay, the moment you convert to seconds, it will be -6. Then we can do the calculation, right? So this should be -6. So that is why this is 10 to the power -6, and then this will be actually 10 to the power 9. And then I think, okay, if we do the calculation, then we will be getting the same thing. So finally, we will be getting this, right? Let me know if that is clear or there is any doubt here. I hope that is fine, right? Okay, now let's just solve more questions. Or do you want me to solve this tomorrow? Because anyway, we will be just taking one more class for the sliding window. So let's just solve one or two more questions, then we can solve other questions tomorrow. The maximum window size for the data transmission using the selective reject protocol with n bit. So selective repeat or selective reject, both are the same thing. So what is the answer here? It should be 2 power n minus 1, right? So B should be the answer. 2 power. Okay, this is -1 is in the power, okay? Yeah, for the go back n, it is 2 power n minus 1, and for the selective repeat or selective reject, it is 2 power n minus 1. I hope you know this, right? So, like, I mean, generally the sender and receiver window size is same. And why that is the case, that I already told in the theory, right? I mean, why we keep the separate window, which means, like, let's suppose here the total sequence number is let's suppose anyway, like, let's suppose the total sequence number is Sn. Okay, this could be anything, this could be any number. Then the window size here, okay, if the n bits I'm using, then there are total sequence number that are available with us is 2 power n. But the window size that we keep is basically just 2 power n by 2, which means 2 power n minus 1 here at the sender size, at the receiver size also 2 power n minus 1. Why we are keeping these I mean, things like that? Because there is a scenario that I told you, that what if all it is sending the ACKs and all the ACKs get lost, then it should not wait for something which are duplicate. So this receiver should be waiting for something which is a new data, right? Let me just tell you again that what I mean to say. Let's suppose that you have 0 1 2 3, okay, 4 5 6, okay, these, or maybe 0 1 2 3, these are the sequence number that you have available with you, and then it will repeat. Suppose you send all of them once. Okay, first thing is that can you send all of this once? Answer is no. Why? Because these two zeros or these two ones may get in the air. See, this is 0 1 2 3, and similarly you're sending 0 1 2 3. Now what will happen at the receiver? It will not be able to distinguish that this is the first 0 or this is the first 0. What if that this 0 get delayed, right? What if this 0 did get delayed? So that's why you can definitely not send some packets which is like this, which means if the sequence number is repeating, then you cannot definitely send. So you have to send in one window, you have to send something where the sequence numbers are at least not repeating, right? So which means you have to send something like this, at least. Like this is the minimum thing that I'm saying. Now let me just show you that why you cannot even send this. Why you cannot send this? Because if you send this 0 1 2 3 and it receives all of them, and what if whenever it sends the ACK, the ACKs are getting lost, okay? ACKs are getting lost. Then the sender will not get to know whether the ACK will get lost or the data get lost. Then it will resend. This is the retransmission of 0 1 2 3, right? This is the retransmission. And then this receiver will say that, see, I am waiting for, see, initially also it was waiting for 0 1 2 3, receiver is waiting for 0 1 2 3, right? 0 1 2 3, but it got this duplicate 0 1 2 3, but by mistake it does not know that whether it is a duplicate or not, so it will accept it, right? It will accept those duplicates. So that is why the receiver should not wait for something which the sender can again send in the retransmission. So basically that's why we keep it something like this, that receiver should always be waiting for a next set of numbers, which means if I'm just sending, let's suppose this is 0 1 2 3, but if I'm just sending 0 1, and if this 0 1 ACK get lost, okay, they send the ACK, it get lost, whenever it is retransmitting 0 1, then receiver should wait for something different. Receiver should wait for 2 3, and at that time it will recognize that, okay, this is the duplicate, this is a duplicate, like that. So that's why we keep it half and half, right? I hope you remember it. Okay, so now this is the next set of questions that we will be solving tomorrow. Okay, let me know if there is any doubt that you have. Yes, Sumant, that is correct. Okay, I hope things are clear, and then we will be solving these questions tomorrow. And tomorrow, if time permits, I will be solving some error control methods also, which is having distance and CRC. So thank you everyone. Take care. Bye bye.